Assalamu alaikum warahmatullahi wabarakatuh. Hello everyone. My name is Walid Saeed and I am from Group 9. And today we are presenting the manual losses in a pipe. And also have my two class my group mates, which Ibrahim Omar and Muhammad Amin. So I will start with the abstract. Although they often account for a major portion of the head loss, especially in process piping, the additional losses due to the entries and exit fitting and bulbs are traditionally referred to the manual losses. These losses represent additional energy dissipation in the flow, usually caused by secondary flows induced by curvature or recyclation. The manual losses are any head losses present in addition to the head losses for the same length of straight pipe. The objective of this experiment to determine the loss coefficient KL valve and manual head loss HLM in a pipe components fittings for different water flow rate, pipe diameter, and pipe width. Moreover, the energy losses in pipe flow rate flows are formed by friction between the fluid and the pipe walls, as well as internal friction between fluid particles. Moreover, the manure, which is also called secondary head losses, occur in any points in a pipe system where streamlines are not straight, such as pipe junctions, bends, valves, contractions, expansions, and reservoir inlet and outlet. Moreover, the manure head loss will be measured through a pipe segment with numerous bends, transstation, and fittings in the experiment. Moving to the theory, the flow in pipe system different flow rate may require to pass through a variety of fittings, bends, or upper chains in area 1. Additional head loss, called as a manual head loss, are encountered primarily as a result of flow separation, also by simplifying the Bernoulli equations between 2 points for the horizontal Z1 equal to Z2 pipes. The pressure loss B and total head loss could be determined as the follow, as you can see equation 1, and we derive these equations. We have equation 2, equation 3, 4, and last one, the 5. And whereas the B1 minus B2 represent the pressure drops between 2 points BA. And we also have density of flowing medium. Also, we have the G gravity consists of, which is the constant 9.81. We also have the V1 minus V2, which is the change of velocity of flowing medium from points 1 to points 2. Also, we have the HLT, which total head loss. We have HL, the major head loss. Also, we have F, the coefficient of pipe friction. We have L, which represents the length of the pipe. DI, international diameter of pipe, internal diameter of pipe. V for HL is speed of flowing medium of the tested pipe. HLM, which is the manual head loss. V for the HLM is represent the speed of flowing medium in the vicinity where the manual loss occurs. We have also KL, losses coefficient associated with the HLM. Also, the last one we have H1 minus H2, which represent the definition heights in manometer between points 1 and points 2. Moreover, the value of KL strongly depend on the geometry of the components considered, as well as the fluid properties, include the RA, and the mathematical function of them can be expressed as the follow. As you can see, KL equal to geometry array, which represent equation 6. In many practical application, the RA is big enough that inertia effects dominate the flow through the components, with viscous effects playing a major role. Moreover, the pressure drops and head loss are commonly found corresponding directly with the dynamics pressure in a flow domain by inertia factors. As a result, in fully developed pipe flow in the friction factors F for very large array is independent of RA flow through by flowing through the pipe components fittings exhibit the same condition. As a result, in most practical circumstances, the KL for components is simply function of geometry. The KL value and HLM in pipe will be determined in the experiment for various water flow rate, pipe diameter, and pipe beds. Also, the following is description of each of the geometric tests. As you can see here, the value of KL for the fluid flows through sudden expansion and contraction can be obtained by considering the continuity, which is represent equation 7, momentum, which represent equation 8, and energy equations between points 1 and 2, which represent equation 1. For the control volume shown in figure 2, the resulting three governing equations are the following. As you can see shown here, equation 7 and equation 8. Those equations can be rearranged and give the theoretical KL for a student explanation inlet also. As you can see here in the equation 9, whereas the theoretical KL for student connection can be expressed in equation 10, as you can see here. Moreover, a student explanation and student contraction, K for student explanation and contraction circle ducts, notes the losses for a student explanation are based on speed flowing medium at region 1, whereas for student contraction are based on a speed flowing medium at region 2. The second one is elbow pipe bends and pipe branches. The valve of HLM and KL for the flows involving pipe components such as elbow pipes, bends, and pipe branches could be determined experimentally using the equation 3 to the equation 5. And whereas the B1 represents the pressure small cross section of upstream, V1 velocity of small cross section upstream, AI1 which is represent cross sectional area for upstream, calculated using the internal diameter of pipe. V2 pressure at small cross sectional downstream, V2 velocity of small cross sectional downstream, and also AI2 cross sectional area for downstream, calculated using internal diameter of pipe. For the last part, for me, the parts, as you can see here, the device, which is, and this one is indicate the tested pipe section, and this one outlet valve, and for these valves, which is represent inlet valves, and this one for the pipes 2 tube manometers, and for the down section, which is manometer tube, and this one figure 1 is represent the pressure measurement of test bench. Thank you so much.
Assalamu alaikum and hi for everyone. My name is Abdurrahim Omar. I'm from group 9. So I would like to present this part. So regarding the methodology of this experiment, we need to open completely for the inlet valve by turning to its anti-clockwise direction of the tested pipe section. Also, we need to turn on the main switch and the pump. The manometer tubes from the inlet flowing pressure and the outlet flowing pressure of the tested pipe sections were connected to the 2-tube manometers. So the first reading with a maximum flow of H1 and H2 2-tube manometers was recorded. And the time taken to collect the 3-liter volume of water at the tank was recorded to calculate our actual flow rate. The opening of the outlet valve was reduced for the second reading of the experiment. Furthermore, we need to get the values of H1 and H2 at the 2-tube manometers were recorded, and the time taken to collect 3 liters of a water tank was recorded again. Also, the opening of outlet valve was reduced, and the steps of the manometer reading and the data for actual flow was repeated for another 3 different values of flow rate. The procedure was repeated for other tested pipe.
Okay, so for the result, here we have the first table, which was the sudden enlargement and the sudden contraction. So here at the first one we have when the pipe is fully opened. So you can see here when the 3 liters was filled in only just 3.1 seconds. And as we go down the table, you can see it's getting slower and slower because we're closing the pipes gradually. So you can see here, first one, the flow rate is 58 liter in per minute, and also it's getting lower and lower gradually. Same thing for the sudden contraction. First one, it takes about 5 seconds. Of course, here you can see that it's slower, like comparing to the sudden enlargement, because the pipes are getting smaller, and you can see they are inversely proportional. So when the pipe's diameter decreases, the pipe losses increase, and it's getting slower. So that's why you can see the sudden enlargement has faster times than the sudden contractions. Also, here is the Y type and the T type. Here we have the Y type. At first it's 5.22 second, while the T type first one is 5.63 second. Also, as I said, because the Y type is only like 45 degree angle, while the T type is 90 degree angle, so the losses is more, which leads to slower flow rate. This is the last one, which is for the pipes 90 angle, 90 bend, and the third one is 45 angle. Here it's only 2 liters, with the 90 angle varies between 3.69 seconds to 16 by 97 when we are closing the pipes gradually. The 90 bend have like slower results, because you can see the last one in the 90 angle is almost 17 seconds, while the last one for the 19 bend is almost 23 seconds. And for the 45 angle, like in the average, have the best flow rates. For the first one it's 32.5, and all to the last one, which is 7 liters per minute. Okay, so for the first one, here we are talking about and calculating the losses. In the result, you can see we were just calculating the delta H in the manometer between H1 and H2, while here we are calculating the losses, which is the formula. It's delta P over rho G. As you can see, the H1 and H2 in the results describe the pressure, because as we know, the manometer like calculates the pressure. So here we start with the first one. In the sudden enlargement, the losses varies in the first one between 3.77 times 10 to the power of minus 7 up to 4 to the 10 times 10 to the power of minus 8. As you can see, where the losses is getting lower and lower. Also in the sudden contraction, it's going from 5 times 10 to the power of minus 6 to 2.95 to the times 10 to the power of minus 7. Here we have the second table. The Y type is lower compared to the sudden enlargement and sudden contraction, which is the first one 2.7 times 10 to the power of 96. up to 8.15 times 10 to the power of minus 8. While the t-type starts from 3.7 times 10 to the power of minus 6 up to 3.2 times 10 to the power of minus 6. So as we can here see, when it's slower, when the velocity is slower, when we are closing the pipes gradually, the losses is getting lower because the velocity is directly proportional to the losses due to the formula K times V over G. This is the third table, which is for the 90 angle, 90 bend, and 45 angle. The first one is 4.6 times 10 to the power of minus 6 up to 1.4 to the 10 of the power of minus 7. Second one here is the 3.4 to 9.2 times 10 to the power of minus 8. And the last one here is 4.2 times 10 to the power of minus 6 to 2 times 10 to the power of minus 7. So the second point of discussion is what's the difference between the theoretical value and the actual values we have. So the theoretical value is the value the scientist expects from the equation, assuming perfect or near perfect conditions, while the actual values is the one they have and they calculate in the lab. So, and of course it's the value that they take rather than the theoretical value, which is just taking something approximately. The third point is like I was explaining right now, the velocity and the pipe roughness and the diameter and how they affect the head loss. So the velocity and the pipe roughness is directly proportional, so when they increase, the head loss increase, while the diameter is inversely proportional. And that's why what we saw in the enlargement and the contraction in the pipes, and why it was a higher flow rate in the sudden enlargement. The last point here is what's the most factors that affect the experiment. Of course, the most factor is the human errors that happened in the lab, and like most big companies and industries do, the most effective way is to automate the operation to minimize the errors.
Regarding the conclusion of this experiment, to sum up, I think we have achieved our purpose for this experiment, which is to determine the loss coefficient on a minor head loss in pipe fittings or components for different water flow rate, pipe diameters, and pipe bends. All of them have been solved. In this experiment, we can identify the effects that contributed to the value of loss coefficient, as when the water flow rate increasing, the pipe diameter decreasing, and the length of the pipe bend is also increasing. As a result of that, in a higher value of loss coefficient. Furthermore, we can identify the errors occurred during the experiment, which are influencing the inaccuracy of data. Systematic error and barrels error are the main contributors. For instance, the eyes are not perpendicular to the scale. The stopwatch is asynchronous. Moreover, we can overcome any problem during the experiment for being more careful and focused during the experiment. So that's all. Thank you.